So I'm done talking about definitions of torsion. And so what is the Alexander polynomial? If K is, a knot in the 3 sphere, then I can form S3 minus K, and I can calculate its first homology, and I get Z, but I prefer to write that as a cyclic group, because now I want to form the group ring of the integers, and of course that's Laurent polynomials in T. Well, there's the Hurewicz mapping, which is on 2, and then we can take the kernel of this, and then there's a cover S3 minus K infinity over S3 minus K, whose the image of its fundamental group is exactly the kernel of this map. And because that's a normal cover, that means that that Z acts on this cover as depth transformations. Okay. So now, what I can do is I can realize that in homotopy theory, S3 minus K is a 2 complex. And as a 2 complex, so for instance, if your knot was the trefoil, like this, then the 2 complex you would get, and you could always do it with one vertex, would have 2 edges, X and Y, and then one face, which is a pentagon, which has X like this and Y going like this. And now, because the cells are all simply connected, they lift. And that gives me a decomposition of the infinite cyclic cover as a CW complex. And here's the deal. K, S3 minus K infinity, and this is with rational coefficients. This is a free module over the PID, which is Laurent polynomials with rational coefficients. A mistake that topologists often make is they stick with integer coefficients, and then it's no longer a PID, and so it's something a little more complicated. And then, of course, the same thing is true for all the chain groups, that they're all free modules. And then the boundary operators turn out to be linear with respect to the lifting, basically by uniqueness of lifting. I never said what the Alexander polynomial is, so I'm going to say it now. The Alexander polynomial is the order of H1 of S3 minus K infinity with rational coefficients as an ideal over T inverse. So if you just present it and then take the determinant of the matrix you presented it with, a square matrix, that's the Alexander polynomial up to a unit. It's just the order of that module. And then, then this is Milner's big theorem that the torsion of the chain complex corresponding to the infinite cyclic cover is the Alexander polynomial of K divided by 1 minus T. And that's because this is actually this presents the homology of that because there's nothing higher, and then the extra 1 minus t just comes from understanding this map, which is trivial. And that's the Alexander polynomial that's right west of torsion. So, next. So now it's going to get a little more flamboyant.
So in this theorem, you can use any chain complex you want.
Well, here, by the way, the chain complex has to come from a cellulation, and then the volume basis has to be given by the cells.
Right, but the cellulation also has to be, I suppose, at least compatible with the Z action and so on, right?
Yeah, and so you always lift it. Otherwise, you're not going to get a basis over QTT inverse. But basically, whenever you take a cover, this is what you do. You triangulate the base, and then you just lift, and that's your volume basis.
So you do this with any finite triangulation.
Yeah. And you could do this like with any cover too, only now you're over the group ring of the cover, and then it might not be a PID, and then you might have to do something, right? So three manifolds are classified, and the first thing you do, given a three manifold, is you cut along spheres that don't bound balls, and then you fill in the balls to get a collection of prime three manifolds, and that decomposition is unique. And then what you do is you cut along incompressible tori, sort of a maximum collection of incompressible tori that are parallel to one another, and then it falls into two pieces. One piece is the characteristic submanifold, which is a Seifert fibered space, and that just means it's a glorified surface. Seifert fibered space is one that can be seen as a union of circles so that there's barely any singularities. There's finitely many fibers where it is not a fibration. And then the other piece is hyperbolic. And the other piece is a finite volume hyperbolic manifold, and that hyperbolic structure is unique. And so the volume of that manifold, that hyperbolic part of that manifold, is a topological invariant. Okay. And then the volume conjecture says that you can compute the volume of a hyperbolic knot from the growth rate of evaluations of the colored Jones polynomial. Okay, so where do you get the colored Jones polynomial? There's a sort of canonical deformation of the universal enveloping algebra of SL2 so that it's a quasi-triangular Hopf algebra. And what this means is that you have R that lives in some reasonable completion of the tensor product of this guy that satisfies the quantum Yang-Baxter equation. And now the Jones polynomial comes from representing your knot as a sequence of events in the representation theory of UQSL2 that can be written down in terms of some canonical operators. Okay, so you have to open the knot up, and then, oh, wish me luck, huh? And then you open it up like this, and say we label it with the fundamental representation of SL2. This is for the Jones polynomial. And now what happens is there's an event which is a minimum, and then this is something that corresponds to the R matrix, and then there's another event that corresponds to the R matrix, and then there's a maximum. And when we get here, this is an intertwiner from this irreducible representation of EQSL2 to this irreducible representation. And then you know by Schur's lemma that it's got to be scalar multiplication, and that scalar multiple, that is J2 of K, right? But then there's an iterative process that, and people didn't understand that this was actually recursively defined invariant at first. People, I guess, people would always tell me that the colored Jones polynomials are all, their behavior is transcendental, they're not related to each other. And people would say that to me over and over again, and I didn't believe them. And so finally I did something about it. And so now what I can do is I can label now with the kth irreducible representation, and that's, maybe I could call that nth irreducible representation, and that's J n. Okay, that's the irreducible representation of dimension n. And now the conjecture is that the hyperbolic volume of S3 minus K, and I'm going to mess it up. Where's the 2 pi go? Over here is the limit as n goes to infinity of the absolute value of the colored Jones polynomial of K, where we evaluate Q at e to the I pi over n divided by 2 pi n, and we have to take the natural logarithm. Whew. Okay, and that's the volume conjecture. Okay, and it's pretty resistant. So people first proved it for the figure 8 knot, and then some people struggled really, really hard, proved it for like a couple 5 crossing knots, and then Rollins proved it for an infinite class of knots. But to this day, it remains open. But in fact, this is an iterative process. You're taking a particular object and really you're plugging it into just using the irreducible representations. For each n, there's an irreducible representation, rho n, from